Hello everyone. Today we are going to explore another fundamental data type in Python, the list. If strings were like DNA sequences, then lists are like a collection of many DNA sequences or codons or gene IDs grouped together. A list is basically an ordered collection of items. They are created by using square brackets. Unlike strings, which only hold characters, lists can hold anything: DNA sequences, numbers, or even a mix of both. Here I have written items inside square brackets separated by commas. For example, if I write ATG, CGT, TTA within square brackets, that could represent a list of codons. If I write BRCA1, TP53, EGFR within square brackets, that could represent a list of gene names. And if I write numbers like 250, 300, 500 within square brackets, those might represent a list of read counts. In bioinformatics, we rarely deal with just one sequence. Usually, we work with hundreds or thousands. Lists let us keep related information grouped together: all the gene names, all the read counts, or all the codons. For example, when you read a FASTA file in Python, the data often comes as a list. Just like strings, lists are also ordered. This means every item has a position, also called an index. Positive indexes start from 0 on the left, so ATG is at index 0, AAA is at 1, CGC is at 2, and TAG is at 3. Negative indexes start from minus 1 on the right, so TAG is at minus 1, CGC is at minus 2, AAA is at minus 3, and ATG is at minus 4. If I write DNA underscore list and within square brackets I put 0, I am getting the very first element from the list. And if I write DNA underscore list and within square brackets I put minus 1, that gives me the very last element. Indexing makes it easy to access items from either end of the list. Now let's take a look at list slicing in Python. Just like string slicing, list slicing also allows us to extract a portion of a list. The general format is: I write the list name and inside square brackets I put the start index, then a colon, then the end index, and optionally another colon for the step. The start index is included and the end index is excluded. For example, consider the list DNA underscore list with items ATG, AAA, CGC, TAG, GGA, TTA, and CCC. The positive indexes go from 0 to 6 and the negative indexes go from minus 7 to minus 1. If I want the first three elements, I write DNA underscore list and inside square brackets I put 0 colon 3. This will include 0 but will exclude 3, and therefore it will give us elements at indexes 0, 1, and 2, and the output will be ATG, AAA, CGC. If I want elements from the third element all the way to the end, I write DNA underscore list and inside square brackets I put 2 and a colon. This will return elements from index 2 to the very end. This gives CGC, TAG, GGA, TTA, CCC. We can also use a step. For example, if I write DNA underscore list, inside square brackets I put 0 colon 7 colon 2, Python will take every second element starting from index 0 up to index 6. The output will be ATG, CGC, GGA, CCC. Finally, we can reverse the list by leaving the start and end empty and using a step of minus 1. So I write DNA underscore list colon colon minus 1. It will return the list in reverse order. Slicing is a powerful tool because it allows us to easily access parts of a list, skip elements, or reverse it, all without changing the original list. If you are having any doubts understanding list slicing, I would suggest you to go and watch my video on strings and go through string slicing. Now let's move to Jupyter Notebook and take a look at each of the concepts that we have discussed till now in our PowerPoint slides. Here I am writing DNA underscore sequences equals, and within square brackets I am putting 4 items: ATG, CGT, TTA and GGC. This creates a list of 4 DNA fragments. Then I am printing the variable DNA underscore sequences. The output will show the list exactly as it is: ATG, CGT, TTA and GGC inside square brackets. So this demonstrates how to create a list and see all its items at once. Lists are containers for multiple elements, and printing them helps confirm that all the intended data is stored correctly. Here I am writing type and passing in DNA underscore sequences. This tells us what kind of object it is. The output will say class list, meaning Python recognizes this as a list. Checking the type confirms that our variable is indeed a list. This is important because it tells us what operations we can perform, like indexing, slicing, or adding new items. Now I want to create two variables. First, I am writing first underscore codon equals DNA underscore sequences, and within square brackets I put 0. That gives me the very first element in the list, which is ATG. Then I am printing it, so the output will be ATG. Next, I am writing last underscore codon equals DNA underscore sequences, and within square brackets I put -1. That gives me the very last element in the list, which is GGC. Then I am printing it, so the output will be GGC. This shows how to access specific items in a list using indexes. Positive numbers start from the beginning, negative numbers start from the end. Indexing is essential for retrieving or modifying precise elements. Here I am redefining DNA underscore sequences with more items: ATG, CGT, TTA, GGC, AAC, CGA and TTG. Now I am showing some slicing examples. First I am writing first underscore 2 equals DNA underscore sequences, and inside square brackets I put 0:2. That means start at index 0 and stop before index 2. So I get the first two items ATG and CGT. When I print it, the output will be ATG and CGT inside square brackets. Next I am writing from underscore third equals DNA underscore sequences, and inside square brackets I put 2:. That means start from the third item and go until the end. So I get TTA, GGC, AAC, CGA and TTG. When I print it, the output will show those 5 items inside square brackets. Then I am writing second underscore 2 underscore fifth equals DNA underscore sequences, and inside square brackets I put 1:5. That means start at index 1 and stop before index 5. So I get CGT, TTA, GGC and AAC. When I print it, the output will show these 4 items inside square brackets. Slicing allows us to extract portions of a list without changing the original data. It's a powerful way to work with subsets of your sequences, whether you want the first few, the last few, or any specific range. Here I am creating a list called mixed underscore list. Inside square brackets I have the string BRCA1, the integer 42, the decimal number 3.14 and the boolean value true. When I print it, the output shows all four items together inside square brackets. This demonstrates that list can hold different data types together. You can combine strings, numbers, and logical values in one list, making it extremely versatile for storing heterogeneous bioinformatics data. Here I am creating a nested list called nested underscore list. Inside the outer square bracket, I have two inner lists. The first inner list has ATG and CGT, and the second inner list has TTA and GGC. When I print it, the output shows both inner lists grouped inside square brackets. A nested list is a list within a list. This structure is useful when you want to organize data in rows or groups. Each inner list can be treated as a separate collection, making data management easier. Beginners often confuse between strings and list and where to use which one. Here I am creating two variables. The first one is string underscore example equals ATG inside quotes, so that's a string. When I print it, the output just shows ATG without any brackets. The second one is list underscore example equals, and inside square brackets I have ATG and CGT. So that's a list. When I print it, the output shows ATG and CGT inside square brackets. This highlights the key difference between strings and lists. Strings are sequences of characters while lists are collection of items. Understanding this difference is fundamental because it determines how you manipulate and work with your data. Now we know that we can efficiently store a single DNA, RNA, or protein sequence in Python as a string. So you might question that why not use strings for storing multiple sequences as well? Let's take a look at why storing multiple sequences as a string is a bad idea and how does list proves efficient in doing this. Here I am creating a string variable called multi underscore seq underscore string. If I want to store multiple sequences in a single string, I can put them together separated by commas. So I have written ATGCGT, TTAAGC, and GGATTA all inside quotes as one string. Next, I am printing the variable multi underscore seq underscore string, and the output will be ATGCGT, TTAAGC, GGATTA. Now if I want the second sequence, I have to use slicing on the string. Here I am writing multi underscore seq underscore string, and within square brackets I am writing 7 colon 13, which picks the characters starting at index 7 up to index 12, and the output will be TTAAGC. You can see how tricky this is. I have to manually figure out the start and end positions, and if the sequences are not all the same length and the DNA sequences are very long, which they are in reality, then this becomes very error prone and hard to manage. Next, I am creating a list variable called multi underscore seq underscore list. If I want to store multiple sequences properly, I put each sequence as an individual item in square brackets. So I have ATGCGT, TTAAGC, and GGATTA as separate item inside the list. Next, I am printing the variable multi underscore seq underscore list, and the output will show each sequence separately. Now if I want the second sequence, I can simply write multi underscore seq underscore list, and within square brackets I can write 1. I can also modify any sequence or loop through all sequences easily. We will see these in the upcoming videos. So this shows how list makes storing, accessing, and managing multiple sequences much easier and clearer compared to using a single string. Let's quickly recap what we learned about list in Python. A list is an ordered collection of items. Unlike strings, which only hold characters, list can store any type of data, DNA sequences, numbers, or even other lists. List can be indexed and sliced just like strings, making it easy to pick specific items or ranges. But unlike strings, lists are mutable, which means we can change their contents. We will explore more on list mutability in our next video. Most importantly, lists give us a simple and powerful way to store, access, and manage multiple sequences in bioinformatics, whether they're codons, gene names, or read counts. So whenever you are dealing with more than one piece of data, think of using a list. Thank you so much for watching this video. If you found it helpful, don't forget to give it a thumbs up, leave a comment with your question or feedback, and subscribe to the channel so you don't miss the next video in this Python for Bioinformatics series. See you in the next one.